In the mid-14th century, the University of Paris became the epicenter of an intellectual rebellion that broke with Aristotelian dogma. Medieval science operated under a specific constraint. Natural philosophy was downstream of language. To change how the physical universe functioned, thinkers first had to change how words referred to reality. The intellectual weapon they deployed was nominalism. Nominalism is a philosophical system that strips away abstract metaphysical concepts, demanding that language point exclusively to observable, singular things. The figure at the center of this shift was Albert of Saxony, a master of arts at Paris whose logical works redefined the boundaries of natural philosophy. Albert weaponized nominalist logic to strip medieval physics of its metaphysical bloat. By doing so, he forged the mathematical mechanics that preceded the Renaissance. Historical accounts frequently credit John Buridan as the undisputed master of 14th-century Parisian physics and the originator of impetus theory. Impetus is the concept that a moving body acquires an internal motive force. Against Buridan's reputation, modern histories often relegate Albert of Saxony to the role of a pupil or a compiler of his master's notes. The manuscript record shows they were peers. Albert composed his works concurrently, and Buridan modified the final versions of his own commentaries in response to Albert's critiques. Albert possessed a distinct advantage, a deep integration of English logic. He fused Parisian physical models with the mathematical innovations emerging from Oxford. Albert acted as the primary engineer of a new, unified scientific network, building the institutional structure that exported this new physics out of Paris and across Central Europe. The foundation of this network is Albert's masterwork, the Perudulus Logica. Here, he applies a strict Ockhamist semiotic approach. Spoken terms are signs subordinated to mental concepts, and they refer exclusively to singular physical things, a property known as suppositio. This strict rule for language forced a break from Buridan, who argued quantity was an absolutely real, independent thing. Albert launched a nominalist attack. Treating quantity as a separate entity introduces metaphysical bloat, complicating physical equations with unnecessary variables. He established a new rule: quantity and relations do not exist independently. They are merely dispositions of a substance, or the result of an act of the referring soul logically comparing two objects. This linguistic distinction determined his natural philosophy. If quantity is not a separate thing, then phenomena like condensation and rarefaction are explained purely by the local physical motion of particles, rather than an invisible force. The result is a lean, modular physical framework, devoid of unseen variables. By cutting away invisible entities in his grammar, Albert forced physics to rely purely on observable matter and motion. To stress test these rules, Albert focused on linguistic edge cases, compiling a volume of logical puzzles known as the sophismata. Albert tackled self-referential paradoxes, like, "This sentence is false." He argued a proposition has its own proper significant, beyond its individual words. Every valid proposition implicitly signifies it is true by its form. Therefore, an insoluble proposition is structurally contradictory and resolves as false. Albert proved that a perfectly regulated logical system could resolve recursive paradoxes. This certainty gave him the confidence to apply the same rule set to the complexities of the physical universe. Armed with this system, Albert moved from linguistic semantics into his commentary on Aristotle's physics. Unlike Buridan, who treated motion as a distinct entity alongside the moving object, Albert applied his nominalist razor to reject this. For Albert, locomotion is simply a physical object shifting spatial coordinates over time. Motion is an event to be measured, not a thing. This introduced the problem of projectiles. If motion isn't a physical substance and the surrounding air isn't pushing a thrown stone, what keeps the stone moving once it leaves the hand? His answer was the virtus impressa, or impetus. He defined this as an internal quality acquired by the moving body, transferred directly from the thrower. He maintained a strict epistemological realism here. Albert stated that determining the nature of this force is a problem for metaphysics. The science of physics is strictly concerned with measuring its observable effects. By removing the abstract flux of motion and defining a measurable internal impetus, Albert created a calculable framework for physical dynamics. This framework confronts the division between terrestrial and celestial spheres. Traditional cosmology required divine intelligences to move the heavens. Albert extended the impetus theory, arguing that the same internal force moving a thrown stone on Earth also propels celestial bodies through space. By rejecting intelligences as mechanical agents, Albert established that the entire universe operated under a single, unified set of physical mechanics. To calculate the system, he integrated the work of the Oxford octupulators. He adopted the mean speed theorem from William Heytesbury, deploying it to calculate uniform acceleration across any moving body. He then applied Thomas Bradwardine's geometrical proportions, mapping the mathematical relationship between an object's motive force and its resistance. Albert merged Parisian theories of force with English mathematical kinematics, creating a system of motion applicable to everything from a falling rock to Jupiter's orbit. To finalize his mechanics, Albert introduced a methodological innovation, boundary condition analysis. He tested his kinematic equations against imaginary, naturally impossible extremes. A prime example is his vacuum hypothesis. While he maintained that a pure vacuum is impossible in the natural world, Albert used the parameter of God's absolute power as a logical loophole to imagine one anyway. He did this to isolate variables. By modeling how impetus would act in a frictionless void, he could observe the pure mechanics of motion independent of environmental resistance. He maintained strict boundaries. Even though these imaginary hypotheses provided mathematical insights, Albert insisted that the science of physics must return to explain the observable, natural order. Albert was effectively running mental simulations centuries before the technology existed, using pure logic as his rendering engine. This synthesis of logic and physics made his textbooks highly sought after across Europe, establishing his legacy beyond the written page. He backed these texts with institutional power. Leaving Paris, he became the first rector of the University of Vienna in 1365, carrying the new physics into Central Europe. His work subsequently eclipsed his predecessors. His commentaries on Aristotle's physics and De Caelo became the authoritative standard, surpassing Buridan's in academic influence and distribution. From Vienna, he tracked this knowledge south. His treatise on proportions and his physics commentaries entered the universities of northern Italy, specifically the curriculum in Bologna. His career culminated in his appointment as the Bishop of Halberstadt. This cemented his status as a towering figure of 14th-century institutional authority. By transforming Ockham's logic into a rigorous, calculable physics, Albert built the intellectual framework later inherited by Galileo, Da Vinci, and the early modern scientific movement.